All right, next we want to look at equivalent or equal fractions. So grade 4 is when students should be able to recognize two fractions as equivalent by using visual fraction models, looking at the number and the size of the parts, even though the two fractions themselves are the same size. So let's look at the pictures here on your screen. We saw a similar picture a few slides ago to represent 1/3, where our whole is the whole square. It's broken into 3 equal size pieces, and one of those pieces is shaded. So that's 1/3. Now you can see if I break each of those 3 pieces in half, that gives me a total of 6 pieces. And so the picture in the middle represents 2/6, and I could break each of those pieces in half again, and now I have 12 pieces, and again the same shaded area now represents 4/12. So looking at the picture, students should recognize that each of those green shaded strips represents the same size, even though that they are rectangles that have been broken into different size pieces. And so they should be able to conclude that 1/3 is equal to 2/6 is equal to 4/12. You could also illustrate that using fraction strips. So these are strips that are broken into different fraction sizes. So we've got a strip that represents 1, and here they've got a strip that represents a half. If you take 3 1/6 strips and stack them right next to each other, you can see that that's equal to 1/2. So they would be able to say that 3/6 is equal to 1/2. And on the bottom, we've got 1, 2, 3, 4, 5, 6 12s. So also they can conclude that 6/12 is equal to 1/2. Okay, in general, if we want to show that two fractions are equivalent or equal without drawing the picture, we can use some algebra. So here is the algebra. A over B is equal to n times A over n times B, as long as n is not 0. All right, so as long as I multiply the numerator and the denominator by the same whole number, I get an equivalent fraction. All right, so let's use that to find a number x such that 10 over 15 is equal to x over 45. Well, hopefully you will notice that 45 is 3 times 15. And so since these fractions are equivalent, that means that that x must look like 3 times 10. Whoops. So we must have x equal to 3 times 10, which is 30. Since 10 over 15 we know is equal to 3 times something over 3 times 15. And I'm sorry, that has to be 3 times 10, right? Okay, so x is 30 here. We can also think of going back the other way. So if I have a fraction n times A over n times B, so the numerator and denominator have a common factor n, well, I can think of canceling that n out and reducing to get a fraction A over B. And so that's what we're doing when we're looking to get our fraction or our rational number in simplest form. Okay, so it's in simplest form if the numerator and denominator have a GCD of 1. That means that they have no common factors greater than 1. So we want to look at these fractions here and try to put them in simplest form. I would recommend that you pause the video for a minute and try these on your own first, and then come back and look at my answers if you're struggling with any of these problems. Okay? So I'll give you a second to pause, and then I'm going to go ahead and start working on these. Okay, so let's think about factoring 12, and 75. So 12 is 2 times 2 times 3. 75 is 3 times 25, which is 3 times 5 times 5. The numerator and denominator have a common factor of 3, and so I'm left with 2 times 2, which is 4, over 5 times 5, which is 25. So this reduces as 4 over 25, and that is in simplest form. 4 and 25 have no common factors other than 1. All right, what about 28ab cubed over 49a to the 4th b squared? Well, I'm going to write 28 as 4 times 7, and I'm going to leave the ab cubed. And 49 is 7 times 7, and I have a to the 4th b squared. So what can I cancel here? Well, I could cancel some 7s. Let me use a different color. I have an a to the 4th over or under an a to the 1st. So I can cancel one of those a's, and this 4th gets reduced down to a 3. And I have a b cubed on top with a b squared on the bottom. So I can cancel the b squared, and this cubed gets reduced to 1, right? 3 minus 2 is 1. All right, so what am I left with here? I have 4 times b on top over 7 a cubed on the bottom. And there are no more common factors there. Okay, what about in C? Well, on top I could factor a 4 out. So I've got 4 times a plus b over the quantity a plus b squared. And we can think of that as a plus b to the 1st. And so I can cancel 1a plus b here, and I'm left with 4 over a plus b. What about D? I have a 3 plus x squared over 3x squared. Well, hopefully you've thought about this one already. If not, pause the video and think about it before you come back to it. Okay, so what do you think? Can I factor anything out of the numerator? No, there's nothing common between 3 and x squared. So there's nothing I can factor out here. So this is already in simplest form. Now what about E? Well, here I do have a 3 in both terms. So I can pull that 3 out front on top. So I've got 3 times 1 plus x squared over 3, and let me switch colors again to show my cancellation. So I can cancel the 3's. Whoops, and I lost an x squared, didn't I? I've still got my x squared down here. Now can I cancel my x squareds? Hopefully what you said is no. I can't cancel those because on top I have a sum. I have 1 plus x squared, not x squared times something. I can only cancel when I've factored the top and the bottom and they have common factors, okay? So this is just 1 plus x squared over x squared. And finally for F, the top is just x squared. On the bottom I could pull a 3 out again, and I'm left with 3 times 1 plus x squared. Let me clean that up a little. But here, that's as far as I can factor the denominator and the numerator. And they have no common factors, right? They have no common factors here. So there's nothing else that I can do. There's nothing to cancel. So this is also already in simplest form. Be careful here. I know that some of you are going to want to cancel these x squareds. Don't do it. Remember that you've got to have your numerator and your denominator factored before you start canceling. All right, here's a couple more. I have y squared plus x squared over y plus x. Well, y squared plus x squared doesn't factor. They don't have any common factors, and I can't write it using FOIL backwards, for example. So the top doesn't factor. The bottom also doesn't factor. And so they have nothing in common. So this is already in simplest form. Now what about h here? So all that's changed is my sign, right? Now I have a minus here. But that does change the factorability of that numerator, right? This is our difference of squares, and so we should use our difference of squares formula to factor this as y plus x times y minus x, and it's over y plus x. Now can I cancel? Well, sure, I've factored the top, and the denominator is already as factors as it can get, and I have a common factor here, y plus x. And I'm left with y minus x. Okay, so how are we going to show that two fractions are equal? We're going to look at two methods for doing that. So the first method is just to put both fractions into their simplest form. So I've factored 12 and 42 in the first fraction, and I factored 10 and 35 in the second fraction, and then I cancel their common factors. So I cancel a 2 and a 3 here, and I'm left with 2 over 7. I can cancel the 5's in 10 over 35, and I'm left with 2 over 7. And since I get the same reduced fraction, or fraction in simplest form, the two original fractions must have been also equal. All right, our second option is to rewrite both fractions with the same least common denominator. So to multiply them by something appropriate on top and bottom so that I get the same denominator in both cases. The least common multiple of 42 and 35 is 210. So I could write, let's see, 42 as the denominator. Let me write this a little more clearly. 12 over 42. I could multiply numerator and denominator by 5, and that doesn't change the equality of the fraction. Oops, not 5 times 60, 5 times 12. I'm looking ahead. Okay, so 5 times 12 is 60. 5 times 42 is 210. And same idea here. So now I'm going to multiply numerator and denominator by 6. So I get 6 times 10 on top over 6 times 35. And that's 60 over 210. And now they have the same denominator and numerator, so the two fractions must be equal. All right, here's a third method. Let's rewrite both fractions with a common denominator. So maybe I could find a better choice for a common denominator than just using the least common multiple. So maybe I'm having trouble finding the least common multiple, and so I just multiply 42 times 35. That's going to give me a common denominator of 1470. And so when I multiply 12 times 35, I get 420 on top. And when I multiply 10 times 42, I also get 420. And so again, I end up with the same fraction, 420 over 1470. And so the two fractions I started with must be equal. All right, so here's a third way, a fourth way. Two fractions, a over b and c over d, are equal if and only if a times d equals b times c. So think about when I write a over b times c over d, I can cross multiply, right? That's what we're doing. we cross multiply and we get AD equals BC. I multiply both sides by D and I multiply both sides by B. Okay, so, whoops, sorry. Let's go back to our fraction. We had 12 over 42 and 10 over 35. 12 over 42 is equal to 10 over 35 if and only if 12 times 35 is equal to 10 times 42. Well, I'll do the right-hand side. I get 420, and so hopefully when I multiply 12 times 35, I get 420. Just for kicks, let's use partial products here. So 12 is 10 plus 2, 35 is 30 plus 5, and I'm going to multiply in the squares. So I get 60, 30, whoops, sorry, 300. Whoops. Oh my goodness. There we go. 50. And 2 times 5 is 10. And I add, right? 300 plus 60 plus 50 plus 10. That's going to give me 420. Okay, so a fourth method is 12 over 42 equals 10 over 35 because 12 times 35 equals 10 times 42 equals 420. All right, so lots of ways to check that two fractions are equal.